The first thing that every single browser is doing is using numerous TCP sessions. Interestingly, Chrome does it way better than, for example, Firefox. Firefox is very simplistic, and this is what all browsers were doing the last time I checked, let's say a year ago. You generate the first request, and as the response starts coming back, you figure out that you need to generate some additional requests, and Firefox would open up to 5 additional sessions. So in total, it will open 6 sessions. You see, this one was waiting till this request completed, and then the next request was sent and the response got back. Firefox would use 6 sessions per host name, and the new sessions would be established only after the initial response is parsed. So you see the green thing here is actually TCP SYN phase. After I start parsing the response, I'm sending 5 more TCP SYN packets to get 6 sessions. For the 7th request, I'm reusing session number 1 here. So you no longer see the green bars until we start opening TCP sessions to other hosts, and at that point, the green bars appear again. As always, style sheets are loaded first, JavaScript is loaded next, and images are loaded last. If you really want to know what individual browsers are doing, here is a really good website that has an in-depth explanation of what each browser is doing. By the way, here is a trick. It says 6 sessions per hostname. It does not say 6 sessions per web server. So I could have, for example, the web server that is known under 5 different names, and I would serve content from one name, images from another name, JavaScript from a third name, and so on and so on and so on. Or I could even serve images from 5 different host names, which is, by the way, called domain sharding. And by that, browser would open more TCP sessions, so I will be able to download more things at the same time, concurrently. If bandwidth is not a problem, but latency is, this will give you better performance. On the other side, Chrome is really interesting. So I went to another domain here. I had to use a different domain. So I went to UCSD. What you see here is what you would expect to see. But the next time I went to UCSD, you see that these initial things are different. They are all aligned here. What's really going on is that Chrome does open 6 sessions per hostname, but it also remembers what's the optimum number of sessions to pre-establish for that hostname. And the second time you go to that web page, it opens, in my case, 4 sessions in parallel. So you get the responses before you would get them otherwise. Yet again, it optimizes the load sequence so that the JavaScript is loaded before images and so on and so on. The next thing that everyone is using these days are persistent HTTP sessions. I already mentioned them in that Firefox waterfall diagram. They were introduced in HTTP 1.1, which was a long time ago, and now every single browser and every single web server supports them, so we can use them. And the only trick is that the browser and the server indicate that they're willing to keep the connection open. So TCP session is not closed after the HTTP response is sent. And so we first save one round trip time, plus we already have the congestion window, which is bigger than the initial 3 packets. And so we actually save a lot on subsequent requests. The only problem is that every time you have a persistent HTTP session, it consumes a worker process in the web server, which on Apache web servers, the worker processes use a lot of memory. Therefore, the major websites hate persistent HTTP sessions because they are using their resources. Browsers love persistent sessions because it allows them to deliver content faster. web farms hate persistent sessions. Therefore, there is this 15-second timeout. After 15 seconds, the web page is usually loaded, so you don't have to keep the session open, and it would close after 15 seconds of inactivity. By the way, there is a new web server that's used by more and more large websites, Nginx, and that one no longer has the worker processes. It has a totally different concept. It is asynchronous event-based web server, and it doesn't care about the amount of TCP sessions it has. It only cares about the bandwidth and the amount of work that needs to be done. Moving forward, one extra step is HTTP pipelining. You see, on a single session, we lose one round-trip time per request, assuming congestion window doesn't kick in. So we send the HTTP request, we get the responses, and there is one round-trip time here. Then we send the next request, and we wait for the response, and here is another round-trip time here. Now, what if we could, because we know what to do, if we could send all the requests in parallel, and then eventually the response would trickle in, and we would only lose one round-trip time waiting, plus whatever amount of time we need to get all the responses back. This looks like a great idea. I'm sending multiple HTTP requests without waiting for the response, and I will send one round-trip time. Well, will I? Actually, we save almost nothing. Because first, we get head-of-line blocking. If we send 3 requests and the first response is large, then the second response will have to wait till we receive the first response. Maybe that second response would arrive quicker on a different TCP session. So we never know what's the optimal sequence of requests. By the way, someone did a really nice measurement a while ago. He was using DSL bandwidth, and latency was 50, 100, 200, 300 milliseconds of the round-trip time. And you can configure pipelining in some browsers, at least on Firefox. You have to do this manually. And his results were interesting. He saw almost no improvement in real-life websites. And he was doing this on numerous websites. So this guy is running real heavy-duty performance tests. He takes like tens or maybe even hundreds in sometimes of websites and analyzes what happens with a certain idea like HTTP pipelining. In his case, there was almost no difference. So pipelining is a great idea, but in practice, it gives you nothing. The next idea that actually works is Google's proposal to increase the congestion window, initial congestion window, to 10, which allows you to send approximately 15K of HTTP response, which is for well-designed web applications more than enough, in a single round-trip time. It is a very simple thing that you can configure on any Linux server in a single command. So this is how you change the initial congestion window for the default route. On Linux server, actually, you can do this for individual prefixes. And it does not impact any firewall, load balancer, HTTP proxy. And it also has minimal impact on the internet. So if you're really interested, go and read the papers that Google developers published, the first one in the sources list. It's already used by Google and some CDN networks. And here are the results from Google's paper. 3 to 6 is a major improvement. 6 to 10 is another major improvement. After 10, they did see some improvement, but not much. If you increase the initial congestion window size to something like 42, you're actually making things worse because sometimes you actually hit congestion in the internet. And so you start getting worse performance because of packet drops. The table down there is the percentage of retransmissions. Finally, TCP fast open. So the idea is that HTTP request is sent in the SYN packet. The moment the server receives the request here, it can send SYN plus ECK Plus, because it knows that the ACK packet will come back, it can send the response immediately. So we have saved one round trip time. We have the first data after a single round trip time. This sounds fantastic. What's the problem? The first problem is that sometimes the first SYN packet will be lost or will be delayed or whatever it is. Sometimes the client will resend the SYN packet. And you wouldn't want to do that if the request is for a payment transaction, for example. This only works for transactions that can be repeated numerous times with no side effects. In web case, these are only the GET transactions. And even GET transactions sometimes have side effects, but let's say that that is then the developer's problem. The other problem is that with traditional SYN packets, we could use TCP cookies to simply stop the denial of service attacks. Because if the ACK packet from the client wouldn't come to the server would not even establish the TCP session. It would first respond with a SYN plus ACK, which uses some hash values it calculates from the user request. So the true TCP session with traditional TCP and TCP cookies would be established only here. Prior to that, server would waste almost no resources. Traditional web servers are well protected, if properly configured, against TCP SYN floods. Here, the problem is that because of the way FastOpen works, if someone starts generating SYN floods, he will also start consuming actual resources on the server because the SYN packets could include actual request data. The countermeasure is FastOpen cookie. The way it works is the first time the client establishes a TCP session with a server, the server sends back a cookie, which is a TCP option, saying, well, we could use TCP FastOpen, and by the way, if you want to use FastOpen, this is the cookie. Then the client would use that cookie in subsequent requests. This sort of reduces the impact of a brute force denial of service attack. Obviously, the client could still send the first TCP SYN packet, get the cookie, and then generate a few SYN requests, and open another session, wait for the cookie, generate a few TCP SYN requests, and so on and so on. You cannot protect the FastOpen enabled server as well as you can protect a regular server. Plus, because of these new TCP options, firewalls, load balancers, all stateful devices in the path would probably bark and drop these packets or remove the TCP options or whatever you configure them to do. This is really a very experimental thing, and Google is probably playing with it, and I'm not aware of anyone else doing anything real with it. Which TCP applications include TCP FastOpen? I think at the moment you have to patch the kernel to have this. Or if you have the browser that has TCP FastOpen and it would work directly with IP stack. I don't think you have any production level kernel that would have TCP FastOpen already included. What tools do you use to analyze that information? All the printouts I have on these slides were produced with either Chrome's developer tools, which you get simply by right-clicking anywhere on the website and selecting from the pop-up menu, inspect this element. And sometimes I use a Firefox extension, which is really good, and it's called Live HTTP Headers. This one gives you a little bit more information. But Chrome's developer tools are really, really good. So they give you more or less all the information you need. What if you could do pipelining on intermediate network equipment? Would that help prevent some of the head-of-line blocking? In enterprise environments, in theory, the answer may be yes. In generic internet environments, the last piece of equipment you control is the exit from your data center, and all the latency is behind that. So even if you could do something in the networking equipment, and I haven't seen any equipment doing anything, it wouldn't help you much. By the way, the proper solution, as I said before, is to implement as much caching as possible. A remark saying congestion window is 10 by default in the latest Linux kernels. Thank you. Is congestion window modification available on load balancers? It depends on actual load balancer product. So I'm pretty positive F5 has something along those lines. I don't want to claim they have it because I'm really not that deep into load balancers, but they do a lot of tricks with TCP sessions. So they terminate TCP session going from the web server out and then regenerate TCP session toward the client, so that, for example, they are also able to do persistent HTTP connection toward the client and establish new connections toward the server as the server tears them down. So F5 can do a lot to help you get better performance. Denial of service with TCP fast open, I think we covered that. Yes, there are some countermeasures like the fast open cookie, but with TCP fast open, it will always be simpler to flood the server with bogus requests. But that's the decision that the web server operator will have to take. Is it more important to shave off one round trip time and get more traffic and, in Google's case, more ad revenue? Or is it more important to protect the servers against denial of service attacks? How effective is it for data centers to employ this type of TCP enhancements on an application delivery controller? If you have an application delivery controller that can actually do that can terminate TCP session, modify it, open a totally different TCP session, or maybe even work on HTTP level, absolutely use this. These are the things that you can do on this level. A lot of things have to be done on the application level, and that's where the programmers have to step in. But there are things you can do on TCP, for example, extending the lifetime of persistent sessions, and absolutely high-end application delivery controllers can help you there. Do you think Windows will eventually support fast open? Not sure. This thing is in very, very experimental phase. I'm not even sure that Google is sure it's a good idea. So I don't expect to see it in Windows anytime soon. To get more information about my webinars, to register for an online session, or buy a recording or the yearly subscription, please visit my website.